gonna bet money that was over.
Computer.
Hello, everybody.
Hello.
Thank you. You have a homework 9 to April 7. Wednesday. And midterm is on Friday. The quiz discussed elastic and inelastic collision. That's what we are studying. And the specific question was give an example of a elastic collision. And it turns out in most of the collisions that we see around us, elastic collisions are very rare. A perfect elastic collision happens in atomic physics. An classic example is what is called quantum scattering. There are many such scatterings where an electron, let's say, electron plus photon collide together and go away. So what happens is that, let's say this is an electron. That's a negatively charged particle. So that's an electron. Atom consists of a proton, neutron, and electron. So electrons are the ones that go around. And photons typically are represented by a wavy line. They come together. They have this characteristic that they have mass 0. So all its energy is it has no mass contribution to it. So it comes in and collides in here, and the electron can go away in this direction. Then sign there means that it is negatively charged. So that's the electron after collision. And the photon could go in the direction. So that's the photon after collision. And that's a perfect elastic collision. The idea was just to point out that elastic collisions are perfect elastic collisions are rare around us in macroscopic systems. Okay, let's review what is elastic and inelastic again. So collisions are we have been using quote unquote collisions as descriptions of systems whenever external forces are equal to 0 and internal forces cancel out. And collisions can be described into 2 kinds. One is inelastic, which we discussed on Wednesday. Inelastic collisions. If there are 2 particles, so you're saying momentum is conserved, so momentum of 1 initial plus momentum of 2 initial. There could be more such particles equal to momentum of the first particle after collision plus the momentum of the second particle after collision. There's also the kinetic energy associated with these particles, and this K1 initial kinetic energy plus K2 initial is not equal to, notice, not equal to K1 final plus K2 final. And we did examples of this kind in the last class. Today we want to talk about elastic collisions. And elastic collisions has this feature that this not equal to sign is released and made equal sign. And let's stick to elastic collisions in 1 dimension. So it's 1 dimension. That means before and after the collision, they are all going along the same line. So everything happens along the same line. Again, very slightly unnatural, but in principle possible. And that is just to make it easier for the analysis. Otherwise, there is an angle theta comes in. The picture that I had drawn for Compton scattering a few minutes back, that's happening in 2 dimensions on the plane of the board. Here, everything will happen along a line on the board. So in that sense, I don't have to write the vector signs, but if I were to still write it, so let's do initial is equal to P1 final plus P2 final. When I write it in terms of the velocity, I will take off the vector signs because plus or minus is the only thing needed when you're traveling in one direction. So it's K1 initial plus.
The camera needs to be moved down a little.
Thank you. I'm concentrating. Okay, thank you. K2 initial is equal to K1 final plus K2. So that's elastic collision. And notice again that we are going to stick to one dimension, but in general, it is possible to analyze in more than one dimension too. Okay. So let's do this more specifically. So elastic collisions in 1 dimension. So we have M1 V1 initial, that's your momentum conservation, plus M2 V2 initial. Notice I've removed the vector sign, everything happening in one direction. So this is momentum conservation. Also that sum of the momentum before the collision is exactly equal to the sum of the momentum after the collision. So it's V1 final plus M2 V2 final. There will be a similar equation for kinetic energy, but before I reach there, let me rewrite this in a particular way just for making it easy. Algebra becomes easy a little. So this is M1. Let me bring in all the M1 on the left hand side and all the M2s on the right hand side. So that's V1 initial minus V1 final. That's equal to, I have to bring the M2 on the right hand side, and I'll write that as M2 V2 initial. That's the V2 initial that goes to the right hand side. It gets a negative sign. So there's already a V2 final with a positive sign, so I write that as negative of V2 final. Negative and a negative makes it positive. That's another way of writing the same equation that was written in the first one. There's also kinetic energy is conserved. So kinetic energy conservation. It should be conservation of momentum and conservation of kinetic energy. I wrote it that opposite way, but it's understood, I suppose. That reads half of M1 V1 initial square plus half of M2 V2 initial square is equal to half of M1 V1 final square plus half of M2 V2 final square. Notice what is the motivation here. Before the collision, there are 2 velocities. Presume that masses are known, M1 and M2 are easier to measure. Before the collision, there are 2 velocities of the 2 masses. And after the collision, there are 2 velocities of the 2 individual masses. If we know the 2 velocities to begin with before the collision, we can do the measurements and we can predict what will happen after the collision. So that's our goal. And for predicting 2 quantities, we need 2 equations. And that's your 2 equations, that's of momentum conservation and the kinetic energy. The second equation is just a rewriting the first equation in another form. But what it turns out that because this is a expression written as a quadratic form in the variables, it is slightly harder to deal with. So we want to manipulate this a little bit, be a little clever, use a trick basically to convert this quadratic expression into a linear expression. Linear means no power of 2 involved. And that's the trick we will use in 2 steps now. And that was the reason why I wrote this in this form to begin with. I wrote all the M1 on the first side. So this is just a trick which reduces the amount of algebra we need to do to analyze this problem. So let me again do the same idea as before, bring all the masses M1 on one side. So that's half of M1 V1 initial square minus of V1 final square. That's what it would read. And on the right hand side, similar to the earlier case, that's half of M2 V2 initial square minus V2 final square. So both the conservation principles we have rewritten slightly differently in the second, in the respective second equations. Now the idea is this is a square minus b square. That's a trick here. This is a square minus b square. It is a minus b times a plus b, right? So let's write it in that form, and we immediately see some cancellations. So v1 initial minus v1 final times v1 initial plus v1 final is equal to minus half of m2 v2 initial minus v2 final times v2 initial plus v2 final. Hopefully I'm still in the board space. Yes. Okay. So this is what happens by rewriting this in this form. Notice that whatever I'm going to box, this boxed quantity is exactly the same as the boxed quantity on the left-hand side of the top equation. And let's say there's a half there. Let me introduce the half also there. Okay. If I put in half in front, maybe I can add a half in the front, right? Let's say here. And with that negative sign, I also box something on the right hand side. There's a half in there. So introduce that half there. And the boxed quantities are all equal because these two boxes are equal. So that means these two boxes are the same. So I can cancel that whole box out, right? So that whole box cancels out on both sides. And what I'm left out with is just a linear equation, V1 initial plus V1 final is equal to V2 initial plus V2 final. So the idea is that whenever you're analyzing elastic collisions, it is possible to analyze it in this using this equation, but it's typically harder to work with, even if you're working with numbers. It is typically harder to get rid of an unknown quantity when you have a quadratic expression. Not very hard, but slightly harder if you want. But if they're linear equations, we can use the linear algebra we studied. All of you must have done a course on it, and it's significantly easier. So we will use this expression instead of the kinetic energy conservation equation, which reads in this form. So these two will be our equation, the first equation that we wrote down here, and the last equation that we sort of derived for kinetic energy conservation. And from that, we can derive a very general expression, and then we will do examples discussing that. So let me very quickly derive the general expression. So let me rewrite the equation. So conservation of momentum now. So this is here. So momentum equation. Now again, rates, I go back to my original form, M1 V1 initial plus, actually, let me write it. The final expression is what are the unknowns. So let me write that as M1 V1 final plus M2 V2 final, because these are the two unknowns I'm looking for, right? So let me write that on the left. And these are the known quantities, V1 initial plus M2 V2 initial. Right hand side is known, and V1 final and V2 final is what I'm looking for. Kinetic energy conservation, even though it is expression in quadratics of V1 initial velocities and final velocities, but we notice that it is easier to think of it as V1 initial minus V2 initial. Sorry, I want to write the final first, right? So let me see. That is a minus V1 final plus V2 final. I rewrote the equation that we derived with all the final velocities to the left and all the initial velocities to the right. So that's minus V1 initial plus V2 initial. Let me check if I did that correct. So minus V1 final plus V2 final. Oh, opposite sign. Sorry. So that's V1 initial minus V2 initial. Okay. So minus, I took all the V1 final to the right and V2 initial. But yes, that's correct. Let me know if you see any mistake in that. Okay, so that's your two equations, and we want to find out what is V1 final equal to and what's V2 final equal to. That's our simple goal in the next 5 minutes or so. And what you do is, these are linear equations, right? So what you would do is, first, let me get rid of V2, right? So I will multiply the second equation. Let me have a reference here. I'm going to multiply by M2 all over, right? First, I'll multiply M2. That brings an M2 here, and then I'm going to subtract them out, right? So that's my first thing I'm going to do. So when I subtract, these two add up, right? So M1 plus M2, V1 final, and plus 0, M1 plus M2, and I'm subtracting after multiplying an M2. So that's M1 minus M2, V1 initial, and I'm subtracting, so this is added, right? So after multiplying an M2, so that's 2 times M2 times V2 initial. That's it. So I get my expression for V1 final as, I divide this out, M1 minus M2 divided by M1 plus M2. I'm keeping this very general, but when we have the numbers, we can just put in the numbers. It's much easier. So V1 initial plus 2 times M2 over M1 plus M2 times V2. I won't be asking you to derive this expression. Earlier, these days we have open book, open resource examination, so you can always use the notes to get substitute these numbers. Even otherwise, before 2 years back, this equations used to be given on the equation sheet that you can use on the exam. At least in my course, that doesn't mean that every exam will allow that. But surely for analysis, you can always have that. And similarly, you can now next, instead of multiplying M2, multiply M1, and this time add. Right? If I multiply M1 and then add, these two cancel out, and it will be V2 final that will be remaining. And what I'll get is V2 final will be equal to, it is, I'm multiplying M1, so it's M1 plus M2 again stays in the denominator. So that is m1 here. So that's 2 times m1 over m1 plus m2 times v1 initial and plus m2 minus m1 divided by m2 plus m1 times v2 initial. That's your expressions for velocity in elastic collision. The two masses come with an initial velocity, which typically you can measure, and you can predict, these equations predict what's going to happen to those masses after collision. With this general expression, we can actually do some simple scenarios. Let's do some extreme examples just to get an idea of what happens in elastic collision. So let's do some very simple examples. So let's consider the case when the masses are the same. M1 is exactly equal to M2. And let me also say that the initial velocity M2 actually is at rest to begin with. So what that means is that you have a mass M2 which is at rest, and M1 is coming with a velocity V1 initial and coming and colliding with it. And the question is, after collision, what happens? We would like to know what happens. Basically, M1 is equal to M2. So I don't have to write M1 and M2. I say these are the same masses. So there are identical billiard balls that is colliding with each other, but one of them is at rest. Right? They have to have the same masses, so one of them is at rest and the other one is coming and colliding with it. What happens? So we have our general expression. So we plug that in. So right, V1 final, what is it equal to? That is in V1 final, that is M1 minus M2 in that first coefficient. That immediately makes this 0, right? So that is M minus M divided by M plus M times V1 initial plus 2 times M divided by M plus M. It doesn't matter what this is because this is multiplied by 0. That's equal to M minus M is 0, so that's equal to 0. So what that means is that this mass, whatever it is, it will come and just stop there. After collision, the first mass will stop, and then what happens to the second mass? V2 final is equal to, we have the expression as 2 times M divided by M plus M times V1 initial plus the second one is M minus M, right? That's 0. Times 0, that's equal to 2 times M, and in the denominator also it's 2 times M, M plus M, so they cancel out exactly, and that's exactly V1 initial. So what is happening is that if there are two identical masses, the first one comes with a velocity, comes to a stop, and the second one goes out with exactly that same velocity. Only in elastic collision that happens. So that's an interesting thing. And if you look up, there is something called, there's a toy called Newton's cradle. What basically it does is, maybe I can draw this. So this is, it's called Newton's cradle. So it's a toy, basically. There is a lot of metallic balls hanging and they're just identical and they're very close to each other. And if you were to actually move the first one to the left and it comes and hits the first one being identical to the next one, it gives all the velocity to the second one, comes to a stop, and that chain reaction keeps going. And if there are 6 of them there, at the end one will be the only one that will come out. So all of them will stay at rest during the collision and the last one will come out. If you were to lift 2 of them and leave it, exactly 2 of them leave from the right hand side. So it's kind of a cute little toy. That's nice to watch, so that you can explain that using this principle. We also see a basketball bouncing from the ground. Let's see if we can explain that. So if we drop a small ball, so this is again an example. What are we dealing with? Let's say we consider the whole Earth, right, as a huge, massive ball, and we have a basketball or a tennis ball dropped right above it from a height h. That's height h, it doesn't matter what's the height. We won't be talking about that, but the point is it comes in and it collides, right? So there is a collision, it comes in, collides with that, and then goes back up. And we would like to know what are the velocities. So that's 1 and that's 2. Mass of Earth is huge, like 10 raised to 24 times that of the basketball. Like mass of Earth is about 10 raised to 24 kgs, 6 times 10 raised to 24 kgs, and mass of a basketball is just 0.6 kgs, right? Mass M1 is 0.6 kg, 600 grams basically to 1 sig digit, and mass of Earth is 6 into 10 raised to 24 kgs. So for all purposes, within 2 sig digits, this is infinity. M2 is infinity. Either you say mass of 2 is infinity, or you say mass of 1 is 0 relative to M2. Since we are interested in the motion of M1, so let's say M2 is infinity to 1 sig digit, right? It's of course not infinity, it's a large, huge number. To 1 significant digit, it's infinity. So in that sense, so again, let's calculate what our, excuse me. I think maybe I'll just mute it. Okay. Okay. So what are the velocities? So let's look for what is the velocity of V1, right, after collision. So V1 final is equal to, remember, M1 is 0.6, or just M1, and M2 is infinity. That's what we are trying to say. So this is M1 minus M2 divided by M1 plus M2 shows up. But what is that equal to? So let me analyze that separately here. M1 minus M2 divided by M1 plus M2. Notice that in the numerator and in the denominator, this is a very small number being subtracted from a very huge number, basically infinity. So we have to think of the limiting scenario in calculus. So we're taking a limit. So that's M2 will dominate in the numerator. So that's minus M2 for all purposes to 1 sig digit. And in the denominator, it is the larger one that dominates, right? So M2 and M2. But after that, after you take that limiting scenario, those two cancel out. So that's equal to minus 1. So if we use that expression here, so that means this is minus 1 of V1 initial plus There was also one more expression there. That's 2 times m2. Is it 2 times m2? Yes, 2 times m2 divided by m1 plus m2. This is again 2 times m2. In the denominator, m1 can be neglected. That's m2. That's equal to 2. But we can say that the Earth is stationary to begin with, right? So that's 2 if you want in the limit of large mass times v2 initial. But 2 is Earth. Let's say this is at rest. So that's equal to 0. So that sets this to be 0. So what that means is that the V1 final, the velocity of the basketball after collision is exactly negative of V1 initial. That means that if the basketball came down and hit the Earth with plus 5 meters per second, it will reverse its velocity after collision and start going in the upward direction. And that's exactly what we see when we bounce a ball on the floor, or on the surface of Earth. What about Earth? We might expect that Earth will actually budge very little. Yes, very tiny bit, but that's really in the 24th decimal. For our purposes, it should be 0. But let's see what happens. V2 final, what's the velocity of Earth after the collision? That's 2 times m1 divided by m1 plus m2. Right, that's what the expression is. So I need space. I can write it here, I suppose. So this is m1, 2 times m1 divided by m1 plus m2. That's the same as 2 times m1. This time I don't have anything to neglect it with, but in the denominator I can still neglect m1. m1 is too small. But m1 is really tiny compared to m2. This is a very small number divided by a very large number, 10 raised to 25, and that's 1 approximately, and that's approximately 0, right? In the limiting case of m2 going to infinity, that's really 0. To one significant digits, that's surely 0. And so that's 0 here. So that's 0 times v1 initial plus m2 minus m1 divided by m2 plus m1. Again, the same idea that you can neglect the smaller mass, or this doesn't contribute to one sig digit. So it's m2 divided by m2. That's equal to 1. So that's plus 1 times v2 initial, which is again at rest, right? So that's equal to 0. So that's equal to 0. So Earth doesn't move when you throw a basketball at it, or when you draw a basketball at it. One can imagine actually that sometimes you think of this thought experiment where you have 1 billion people on Earth, and what if all of the billion people, or about 7 to 8 billion people, all of them come and stood at one point on Earth, and they all jumped off from Earth and came down, and how much would the Earth budge, right? Remember, 1 billion is about 10 raised to 9. Put in another 10, let's say there are 10 billion people, so that's another 10, so that's 10 raised to 1. So that's approximately 10 raised to 10 kg into 100, let's say, each of them weighs, so that's 10 billion. So 10 billion times 100 kg each, let's say. Each person might be weighing on an average 100 kg. That's approximately 10 raised to 12 kgs. But Earth is 10 raised to 24 kgs. Still you're 12 decimals off. So within one significant digit, again, you will not, Earth is not going to move at all. And of course, when humans, unlike basketball, we don't behave like elastic collision. So it would be another equation. But it gives the idea that it really doesn't bother so much. Okay, so that's one extreme where you have M2 to be very large. We can have the opposite also, that M1 could be very large. Like think of Earth moving in space, and it's a small object in space, and what happens to that if it was an elastic collision? Or there is a tennis ball and a car comes and hits it. So what's the motion of the tennis ball afterwards? So let's analyze that. So in this case, let's say M1 is very large. Sometimes instead of saying M1 is infinity, you say not just greater, this means very much greater than M2. M1 is very large compared to M2. So that's a symbol for that. And let's also say that V2 initial is 0. If that's the scenario, what happens? So again, what we have is that you could have a huge M1 and coming and hitting V2, which is really small. So it could be a tennis ball, so that we can approximate it to be an elastic collision. So the idea is that if there was a car coming with a high speed and there was a tennis ball hanging out there or just sitting there, what will be the velocity of the tennis ball and the car after collision? Right. So they collide, and what happens to that? So again, we analyze V1 final, let's say. V1 final is, remember, I erased my equations there. So that was M1 minus M2 divided by M1 plus M2 times V1 initial plus the second term is 0. Notice this time M2 is small, so you drop that down, and M1 and M1 cancels out, so that's 1. So that's equal to V1 initial itself. So these are small, and what is remaining is M1. So M1 and M1 cancel out, so it's 1. So what happens is that the car keeps moving with the same velocity. It doesn't even think of this to be a fly, right? But fly is not really an elastic collision. Think of it as a tennis ball. The mass the car keeps going. It doesn't change its speed at all to within the significant digits we are keeping. What about the tennis ball? What happens to that? That's equal to 2 times M2 over M1 plus M2. Is that? Was that the equation? How? What was the second term? What was this equation equal to? Was it M1 or M2? Can you remind me, guys? I think it was M1, right? Anyone? V1 initial plus M2 minus M1 over V2 initial. Am I writing this correct? Could anyone help?
Yeah, I think that's correct.
Thanks. Yeah, earlier I wrote it as M2 and then I was getting something off. So M1 now, so this is 0 for sure. M2 is small, so I can drop this. And now M1 cancels out afterwards. And what I get is 2 times V1 initial. What that means is that this tennis ball will go with double the speed of whatever the car speed was. So that's probably a slightly non-trivial, that you're moving with 10 meters per second, or let's say 50 miles per hour, and you come and hit a tennis ball that was at rest. And after the collision, the tennis ball will go at 100 miles per hour. And and the car will keep going with the same speed, right? So that's slightly notice this factor of 2 in there. This non-triviality can be exaggerated. So this is a classic demonstration one does, and this is part of the quiz that you will see for the next class that is due on Monday. So it's the following setup. Let me. If it was a normal classroom, typically I do this demonstration in the classroom, but within the camera space, it is hard to capture that. But let me demonstrate that. And in your quiz, you try to answer that question. You do see it in the video, but I'll encourage you guys to try this at home. So the following is a demonstration. You take a basketball. So that's your basketball, and typical, so let's call that 2. So M2 is about 0.600 kg. That's about 600 grams. That's typically what a basketball weighs. And right on top of it, you keep a tennis ball. So that's your 1. And a tennis ball typically turns out to be exactly 10 times smaller, approximately. It's about 0.060. So clearly, M2 is equal to 10 times M1. That's what we want to keep track of. So earlier we talked about very large masses, very small masses. It's in that range. M2 is significantly larger than M1. But now what we are doing is hold a basketball and keep a tennis ball right on top of it and drop it. Right? You just drop it, let go, and keep it aligned so that while it is falling, they stay, their center of masses are aligned with the vertical axis. So they come down and fall, and this is the ground, let's say. Right, so let me, I can go a little farther down. So right, they reach the ground, and that's your basketball when it reaches the ground. But since the tennis ball is still falling, the basketball reaches the ground, has an elastic collision with Earth, and it goes in the opposite direction. Until they reach the ground, they are going to be moving with the same velocity. They will gain velocity, but they'll be gaining the same amount of velocity, because while falling, remember, they are independent of masses. How much velocity they gain does not depend on the mass. So both of them reach a final velocity. And right after collision, the tennis ball is still going down. So the tennis ball is still going down. And the basketball, after rebounding from Earth, is going up now. And that's equivalent to what we talked about just now, that there is a huge mass coming in the opposite direction of another mass going down. And this will get rebounded, but the velocity that one will have after the rebound will be significantly larger. So let's calculate that very quickly. So let's say this is dropped from 1 meter. So if it is dropped from 1 meter, the velocity it will gain is given by half mv square, right? So kinetic energy, remember the energy conservation chapter before this. So the velocity it will gain, both m1 and m2, the amount of kinetic energy or the velocity it will gain is decided by how high you dropped it from. And it's independent of the mass. So that means the tennis ball and the basketball both will gain the same amount of speed. So let me erase this. So it falls from a 1 meter height. So that's where it started from. 1 meter high. So if I were to plug this in, so that velocity is equal to 2 times g times h. That's 2 times 9.8. So that's 19.6. That comes out to be, so that's approximately 4.4 meters per second. 2 into 19.6, 6 square root of 16 is 4. and the rest of the second significant digit comes out to be 4.4 meters per second. So the basketball collides with Earth, but Earth is infinite. So because Earth is infinite, it just flips its velocity. So after the collision with Earth, basketball is going up with 4.4 meters per second. Tennis ball is still going down, and that's going with 4.4 meters per second. So that's your initial velocity, V1 initial during this collision. So this is the collision that's happening. And one will come and collide with basketball because it just collided with it in the opposite direction. And V1 final now, that's what we are interested in. Of course, basketball will also slow down because of that, but we are primarily interested in the velocity of the tennis ball and how high it will go. And that's equal to m1 minus m2 divided by m1 plus m2 times v1 initial. So that's your v1 initial. It's going down, so let me say it is minus. So it's minus 4.4 meters per second. Space there, yes. And this is plus 2 times m2 divided by m1 plus m2 times plus 4.4 meters per second. That's equal to m1 minus m2. m1 was, we said, m1, or I can replace this m2, right? m2 is 10 times m1. So that's 1 minus 10. So that's minus 9 over 11. Right? m1 plus m2 will be 11. And m1 cancels out. And that's minus 4.4 plus this is 2 times m2, which is 1020 divided by 11. That's again 4.4. Notice how the negative signs add up. So both the velocities are going to add up, and that comes out to be equal to, so that's equal to, let me do that. So that's 9 plus 20, 29 over 11 divided by, in times 4.4, 29 divided by 11.
Shouldn't it be 20 minus 9 instead of plus 9?
Because this is a minus sign, right? This minus,
Oh, okay.
that makes it plus, right? So that's the whole point, that it doesn't dissipate, it gets amplified actually. So
All right, thank you.
Yeah, 29 divided by 11 multiplied by 4.4. That's 11.6 meters per second. Let me say that's 12, right? 2 significant digits, that's 12 meters per second. So it came down with 4.4 meters per second, and it went up with 12 meters per second. That's a significant amount of velocity gain. But then it is, how high is it going to go? It was dropped from a height of 1 meter. How high will it go? We again use half mv square is equal to mgh. Masses again cancel, it doesn't depend on who is going up, but we are interested in how high does it go. So h is equal to velocity square over 2 times g. So that's 12 square divided by 2 times 9.8, and that's equal to 144 divided by 19.6, and that's about 7.4 meters. Significantly larger. It was dropped from 1 meter and it is now going 7.4 meters. What's the change in energy if you talk about it? Because final kinetic energy over the initial kinetic energy of the mass of the tennis ball, let's say, is equal to mg h final over h initial. Mg or m1g h final over h initial. M1Gs cancel out, and H final over H initial is 7.4. So the gain in energy is about 7 times, significant. I mean, you're multiplying it by 7, significantly larger. And this also is used in trampoline. You will see in that video how this can be used in when you're jumping on a trampoline, if your friend can help you go higher. And more remarkably, this is used to explain supernova. Supernova is basically a dying star, and as it collapses down, it is basically colliding with the core of the supernova. So you have a supernova, which can be thought of as two objects. So this is the core. It doesn't do anything, but the whole of supernova radially is colliding with the core, and after it collides, it goes back. And that rebound can be significantly larger in energy, and you see it as a huge explosion, and that's what is called supernova. And I'll stop here with that example, and see you guys on Monday. Thank you.
Have a good night and weekend.
Thank you. Blake, you too.
Thank you as well.
Mm-hmm. If there are no questions, let me stop the meeting.